Hello, now we will start with our next video lecture. In this video lecture we'll start a new topic. We will talk about context-free languages. Note that earlier we had talked about regular languages, so let's show the set of regular languages with this set, regular languages. We had seen several different models that were equivalently defining regular languages. These were DFA, NFA, or regular expressions. And towards the last video lectures, we have seen that there are languages that are outside this class, that are not regular. Now, with this video lecture, we will talk about context-free languages. This will be a set of languages that is more general than the regular languages. So we will see that we will define such a set, and we will call it context-free languages. Note that to define regular languages, we had mainly two types of models. One of them was textual model, which corresponded to the regular expressions, and the other one was the automata or the machine model, which was any of these two types of finite automata model, DFA or NFA. For the context-free languages, we will define the context-free languages in a similar manner as well. We will have one model that is, again, textual-based, and another model, a machine model. The textual-based model that will define the context-free languages will be called context-free grammars. And equivalently, the machine model, we will call it PDA or push-down automata model to define the set of context-free languages. We will first start talking about the context-free grammar model. So let's first start with the formal definition of a context-free grammar. We will define a context-free grammar. Let's give it a name G as a for tuple V, T, P, and S. The first term V will correspond to the set of variables. The second term T will correspond to set of terminals. P will correspond to the set of production rules of our grammar. And these will be in the form of the following. We will denote each production rule as follows: A goes to some alpha. In this notation, A is a variable. This is a variable, so A will belong to this set V, and alpha will be a string of variables and terminals combined. String of variables and terminals. And finally, S will correspond to our initial starting variable. Let's give an example for this, for such a grammar. Let's consider the following example. For instance, let's say we have such a rule, let's say is S goes to epsilon. This is a production rule. The variable on the left side is S and alpha is just simply epsilon. So in the right side we can have any string of variables and terminals. And for our next rule we have S goes to 0, S and 1. Let's inspect the right hand side in this rule. In the right hand side we have 0 as a terminal, 1 as a terminal, and S is a variable. Remember that in general, for a general rule, we have A goes to alpha, where A is a variable and alpha is a string of variables and terminals. To make the notation shorter, we can equivalently show this grammar as follows. We can combine these two production rules because both of them are related to the variable S. So in our grammar, the variable S goes to epsilon or 0 S 1. So we can use such a notation as well to describe different production rules stemming from the same variable. So now that we have seen an example context-free grammar, this is an example context-free grammar, we need to talk about how we can define a language that corresponds to a given grammar. For instance, given this grammar, what is the language that it generates? To do this, let's define a couple of things. So let's say that if we have a production rule that says A goes to string W in our grammar, in a grammar G, we will use the following notation: UAV, we use double arrows, goes to UWV, and the meaning of this notation, or the English version description of this notation, is that the string UAV yields the string UW using the rules of grammar G. UAV yields the string UWV. Why? Because we have a rule in our grammar that says that we can substitute the variable A with the string W. That will be the meaning of each rule in our grammar. So if we check this previous example, the rule S goes to epsilon says that you can substitute S with epsilon, or if using the second rule, we can substitute variable S with the string 0s1. We need to generalize this notation for yields, so we will say that we will use the following notation: U double arrow with a star on top of the arrows, V, if U is already equal to the string V, or starting with the string U and using a sequence of derivations, a sequence of this yields operations to arrive at V. Or in other words, I start with the string U, I make one derivation, I So note that U is just some string that consists of some number of variables and terminals. I take one variable inside the string U, and for that variable, whatever rule I want to use in the grammar, I substitute that variable with the corresponding string, and now I get a new string. Let's call it U1. Now U1 is derived from U, and I can do another derivation to arrive at some other string U2 all the way up to UK, and finally this can derive the string V. Now with this we can finally describe the language generated by a given grammar. Let's say we are given a grammar G. We will denote the language generated by the grammar G with L of G and formally define it as any string of symbols from our alphabet sigma, so W belongs to sigma star, such that starting with the starting variable S of our grammar, we can, using a sequence of derivations, arrive at the string W. So basically this says that start with the starting variable of your grammar, do any sequence of derivations as allowed by the rules of our grammar G, and at the end you will arrive at a sequence of terminals. Now we will call that sequence of terminals to be a string inside our language generated by the given grammar G. If we take this example, this previous example, and try to apply these derivations to our grammar, so we have two sets of rules, S goes to epsilon or S goes to 0S1. Let's show some sample derivations with this grammar. We shall start with the starting variable S. Now, I can expand this variable S with the second rule. So I will basically take S and substitute it with this string 0S1. And next I can do yet another substitution. Take this S and again expand or substitute this S with one of its rules, with one of its production rules, for instance 0S1. In this case, keep this initial 0, expand or substitute this S with one of the rules of one of the right hand sides of the rules 0S1, and finally place this existing one. Again, I can say that this string is derived from the variable S. I can do yet another derivation step. Keep these two initial zeros. Substitute this S with one of the production rules. For instance, again, 0S1, and then type the existing ones. I can do yet another derivation rule. Write down the initial 3 zeros. For this S, let's say we now choose to substitute it with this rule that says S can be expanded or substituted with epsilon. So epsilon, and then keep the existing ones. Note that this string actually corresponds to 0, 0, 0, 1, 1, 1, since epsilon means empty symbol in this case. Note that when we say terminal, we mean all the symbols that we have in our alphabet. that we can use to construct strings for a language. Let's try to examine this example grammar further. So our grammar is S goes to epsilon, this is one rule, or S can be substituted with 0S1. Now, given such a language, we have done one example derivation sequence where we start with the starting variable S and we arrive at the string 0001111. What else can be generated through this grammar? Epsilon can be generated through this grammar, just epsilon itself, or just take 0s1 and replace s with epsilon, 01 would be generated. Take s goes to 0s1, substitute that s with yet another 0s1 occurrence, and the final s you can replace it with epsilon, and now we'll have 0011 in our language, or 000111 in our language, and so on. So just from this initial inspection, we can see that if this is our grammar G, the language generated by our grammar G can be defined as 0 to the n, 1 to the n for all n greater than or equal to 0. But usually, formally speaking, such an inspection is not enough to formally claim that this is the language generated by our given grammar. If this is our claim, the normal route is actually, the second step is normally to formally prove that this language description is actually corresponding to the language generated by this grammar G. So usually what we do is write down a formal claim. This is our grammar G. Our claim says that if, let's now call this a language L, W is in the language L if and only if W can be generated by our grammar G. So to prove such a claim, if we can prove such a claim, then this means that the language of our grammar is actually this language, 0 to the n, 1 to the n. To prove claims of this sort, we actually heavily make use of proof by induction. Note that for a claim of this sort, we actually need to prove two separate claims. One is that if W is in the language L, W has this format, then W can be generated by the grammar G. And a second thing is the other direction. If W can be generated by the grammar G, then W belongs to the language. Okay? So we have separated our general claim into two, and we need to actually prove the correctness of both of them. And for the correctness proof of each one of them, we can use induction. We will not show the proof for each of them, but let's just try to show the proof for this first one. So we will use proof by induction. The induction will be set up based on the length of the string W. Okay, so basis step of our induction is, let's take the shortest string inside our language L. Okay, can we show that that shortest string be generated by the grammar G? The shortest string inside our language L is epsilon. So W being equal to epsilon, which is inside our language L, we can easily see that W or epsilon can be generated by our grammar S, by our grammar G. Why? Because there already exists a direct production rule that says S goes to epsilon. Okay, so string epsilon can be generated by our grammar G. For the inductive step, assuming that for some string, for all strings less than some certain length that belong to the language, assuming that for each one this claim holds, that the W, that string can be generated by G, we will try to show that the same thing holds true for a longer string. More specifically, assume for some string W prime, for W prime inside our language L that has this format, a bunch of zeros followed by the same number of ones inside the string W prime, such that for W prime in L, such that length of W prime is less than, let's say, 2k for any integer k, for any positive integer k. Assume for such strings that belong to the language W prime that this claim is true. W prime can be generated by our grammar G, by this grammar. Now, using this assumption, how can we show that the same is true for a longer string W? So, show claim holds for W that belongs to the language such that length of W is equal to 2k. Can we do this? Assuming W is a string inside our language such that its length is 2k, can we show that this W also can be generated by our given grammar G? Now, if length of W is 2k, then W, and W belongs to our language, it has to have the following format. It has k zeros at the beginning and followed by k ones. Now, for such a string, I can write such a string as follows: 0 followed by W prime followed by a single one where W prime is equal to k minus 1 zeros followed by k minus 1 ones. Now, if we inspect the string W prime, it is inside our language L because it has a bunch of zeros followed by the same number of ones, which is the description of our language L. and its length is less than 2k, which means that I can apply this inductive hypothesis, this is our inductive hypothesis, to this W prime. So this implies that, so since W prime is in L and its length is less than 2k, then we know that W prime is generated by our grammar G using our inductive hypothesis. Now, if W prime is generated by the grammar G, let's take a look at our grammar G. Our grammar G has such a rule that says S goes to 0 S1. Since S goes to 0 S1 is a rule in our grammar G, we can simply assume that we replace this S with W prime. Okay, because we know that W prime is generated by G, which means that I can replace S with W prime, which implies that we have S after a bunch of derivations yields 0, W prime, and 1. And note that 0, W prime, 1 string is actually equal to our string W, which implies that S after a sequence of derivation steps yields the string W. In other words, the string W can be generated by the grammar G, which actually proves the first part of our claim, that if the string belongs to the language, to the given language, then the string is generated by G. To complete the proof of this general claim, we normally need to prove this second part as well, but we won't do that in this lecture. This will be left as an exercise. More or less, you can use very similar ideas. You can again use proof by induction to prove this second part of the claim as well. Let's now see yet another example of context-free grammars. For this one, let's first define a language W in 0, 1 star such that W is a palindrome. What does this language include? It includes all strings of zeros and ones such that the string is a palindrome. In other words, reading the string W from left to right and from right to left, they are equal. That's what a palindrome is. Let's just give some examples. So for instance, I can have 0, 1, 0, 0, and then 0, 0, 1, 0. In such a string, for instance, reading the string from left to right is exactly the same as reading the string from right to left. So this belongs to our language L. If we want to further analyze this language L, one question that arises is this language L regular or not? You should be able to notice that to be able to recognize such strings, it might be necessary to have indefinite amount of storage, because we would like to actually store, going from left to right, what the string contains to be able to check the reverse direction as well. And remember that to formally prove that a language L is not regular, we use pumping lemma. So let's do as an exercise, let's try to prove